So hi, everybody. Everybody having fun thus far? Good. All right. So I'm going to go through some of these exciting discoveries. I mostly work with Kepler, and so I'm going to highlight those through what I hope are some really nice visualizations. And some of these movies I made myself, so you'll notice that they're kind of lower quality. But you may be aware, and we just introduced that way, that there's been a recent revolution in the study of extrasolar planets. And again, an extrasolar planet is simply a planet, something that's 13 Jupiter masses or smaller, that orbits around a distant star, so not our sun. And in fact, the recent revolution is quite recent. In fact, as we were just saying, only 25 years ago or so, I'm putting the mark here at 1989, we knew of exactly 9 planets, and those are the 9 planets of our solar system. But even within our 9 planets, we had great planetary diversity. We had terrestrial rocky planets interior, and we had gas giants exterior and ice giants further away, and of course, poor Pluto. and even, we have a lot of science that comes from this. We send out probes. We've done great science, and it occupies our time still today. But even with these 9, we speculated on the formation of the system, which has supposedly been started from the protoplanetary disk of debris around the early sun. And over time, these chunks would aggregate together to form protoplanets, and eventually, in the interior solar system, most of the volatile content, water and gas, has been blown away. So what you're left with is fairly small rocky planets. And then exterior to the said snow line, where there's a lot of gas and there's a lot of ices, you can aggregate much more mass and then collapse all the rest of the gas onto it. You get these gas giants or ice giants. And so this was our tidy formula. This was in 1989. This is how we thought all stellar systems, if they existed, must have formed. So in 1989, it was hard work actually to sell to proposals, grant teams, to look for extrasolar planets. But thanks to the perseverance of a few scientists, a lot of which are actually here at the CFA, we can now count, along with our 8 planets, again, Pluto sadly been demoted, currently 635 exoplanets. So these are not around individual stars. These are exoplanets in multiple systems. And I'll show with a few extreme examples that the diversity of planets and stellar systems that we have found really presents a reality, science reality, that rivals or at least matches our science fiction that we see in movies and so on and so forth. And so it's worth going through a brief history to motivate how Kepler came about and how transiting planets came about. And so this is a great plot. So this is year on this axis, and just the number of planets that have been discovered in a given year. And you can see the pace of discovery has not been constant, but like most emerging fields, it's been accelerating rapidly. In fact, in the early years where you had 1 planet discovered per year, it was groundbreaking. You get that paper out, big news. Nowadays, you kind of have to submit, 5 planetary systems in 1 paper in a month to get in the journal. And honestly, I forget what the tally is. And honestly, I think since I made this figure on Monday, 2 more planets have been added. So this figure always has to be updated. Luckily, there's a website that produces this automatically. So the history of extrasolar planets is actually filled with a lot of really interesting people and great little anecdotes and stories. So I'll give a real Cliff Note version. But I do want to recommend Mike Lemonick's book, Mirror Earth. And he was here, actually. And he's a great guy. He's interviewed many people. I've interviewed myself. And if you want the details of all this interesting people, intimately know them, and how the search for a mirror Earth has gone, it's great. And if you read through it, and then you go to the CFA website, and you look up the faculty here, you'll go to MIT and look up the faculty, you'll find those names that are in the book. And also within this book, so the discoveries that I've helped made are described in detail. So back to our plot of exoplanets with time. The first exoplanet, at least I'll say this is the first exoplanet in homage to Dave Latham, who's here at the CFA, was discovered in 1989, or at least the thing that could have been considered an exoplanet. It has at least a mass of 11 Jupiter masses. So again, this is kind of a large object, but based upon our weak boundary of an exoplanet, it's good enough. But notably, what Dave Latham did was he demonstrated the detection technique that has been used for the majority of these exoplanets, actually, confirmed exoplanets. And the technique that was used there was the so-called radial velocity technique. And so planets obviously orbit around their star in response to the star's gravity. But the planets themselves also have mass. And so the star must respond to the mass of the planet. And so they both are orbiting about a common barycenter, center of mass, right there in the center. And so if we could measure this motion of the star, measure it very precisely, then we can infer the presence of a planet. And so the way that we can do this is we can look at the light coming from the star, which is many colors or many frequencies. And it shifts back and forth as an analog to, if you heard a siren on an ambulance approaching or receding, you get the Doppler shift of the sound. You get the same thing in light. And by carefully monitoring this motion, we could measure this very slow pace of the star moving backwards and forwards. And like I said, this is the technique that has been used for the majority of discoveries up until 10 years ago. So around the early 90s, shortly after, or around the time of Dave Latham's discovery, there were a number of radial velocity surveys looking for bright stars, trying to track their motion. And when they proposed these were tough sells. The people who originally did this, they're trying to get time, lots of time. If they wanted to detect a Jupiter, the time the shift occurs is the orbital period of the planet. For Jupiter, that's 12 years. So if we were expecting to find solar system analogs, you'd have to take 12 years of telescope time. And this is hard telescope time. You need to spend a lot of time on it. So they get proposals. They're like, okay, we'll give you 10 stars. Don't waste our time. But surprisingly enough, it didn't take 12 years. Very quickly, they found 51 Pegasus. Okay, so 51 Pegasus is a bright star. It's a sun-like star. But the reason why they found the planet around 51 Pegasus so rapidly is because it was unlike anything that we see in the solar system. In fact, it was a Jupiter-sized planet. But instead of being, several 5 AU away from 5 Earth-Sun distances away from its star, it was about 1/6 the distance that Mercury is from its star. So the vision is, okay. And so it's really, and to put it in perspective, it's if you took the radius of the star, it's only five stellar diameters away from its star. Okay, that's pretty close, right? And so its year was only 4.23 days. And so it went from one side and back again in 4.23 days. And being so close, it was obviously pretty hot. It was 2,000 degrees Fahrenheit. So that's about 100 times hotter than Jupiter. So this is just north of the melting point of iron at atmospheric pressure. Okay, so this was obviously the first indication. This was a shock. And in fact, it took some time for them to say, oh, I think this is a crazy thing. Because they weren't quite sure. We didn't expect this to exist. How do you get a Jupiter in there? As I said before, it seems to need to form way far out so it can aggregate all this gas that wouldn't be close to the sun because it would be boiled away. And so at that point we said, okay, well maybe the solar system is not representative. Maybe the solar system is in fact rare. And as I'll try to show, in fact, there is great diversity and the solar system is not the end-all. But what importantly 51 Pegasus showed us is that there was this class of systems that we called hot Jupiters for obvious reasons. They were Jupiter-sized. There was a large quantity of these, in fact, that found by these radial velocity surveys, mainly because they're easy to find. Since they had such short orbital periods, you didn't have to dedicate 12 years of telescope time. They just started popping out from these hot stars. And in fact, we realized that fully 1% of sun-like stars played host to hot Jupiters. Okay, so with this in mind, it brought up, the discovery of these brought up an idea for detection that was previously disfavored, and it kind of made it sexy again, is that if these planets are so awfully close to their star, and this animation is trying to show you, how close they really are, you have the chance to catch the planet passing in front of the star from our perspective. And what do we call this? Transit or eclipse, whatever you like. And so this is much like the transit of Venus, which we spectacularly recently saw. But why do we need hot Jupiters to make this method a reasonable technique? And the reason we can see Venus in transit is that it fortunately passes in between us and the sun along our line of sight. But for distant stellar systems that are most likely randomly oriented, so their orbital planes where all their planets sit could be sitting at any angle, there's no preference, we may miss some of these systems. So if we're way over here at Earth and we're staring at a star, then as long as the planet that's orbiting is in this little blue cone right here, we'll see the eclipse. So this hypothetical planet I stuck right here, we would see an eclipse. I'll tell you what I mean by see an eclipse. But if there was another hypothetical planet that was further out in its orbit, there we go, we'd miss it. And so all things being equal, you have a much higher chance of seeing a planet that's much closer into the star than being much further away. And in fact, if you were a random alien staring at the solar system, and you're likely randomly oriented, the chance of being able to catch a transit of the Earth, so in other words, being in a favorable position that a transit could be detected, is 1 in 200. So hot Jupiters, on the other hand, that live some 20 times closer in, that inflates their odds, and they have a chance of 1 in 10. Right? So, of course, we can't really see it like this, right? We can't resolve stars on the sky. And in fact, all we really see in this is a fun movie here, is we get lost in the shine of the star, and the star sinks away as we're falling away. And all stars in the sky, no matter how big your telescope is, for the most part, look like single points of light. Okay? So we don't take a telescope, we don't look up there and we see Venus or a planet crossing over the star, we just see a bright point of light. So how do we know there's a planet in transit? So the trick is that we can still measure the light coming from the star. And so when a planet passes in front of its star, from our perspective, it occludes a small portion of the bright stellar surface. So there it is going up the cross there if you can't see it. And when it does that, the star gets a little bit fainter. Okay? And you get this little profile here. This is brightness as a function of time. You can see it dip down, and then once this planet crosses back over, it rises back up. So if I were to continue this movie, it would wrap back around, and we'd see another event. Let's just say it wrapped around very quickly. And so you see a dip at the orbital period of the planet. So if you see a sequence of these dips in data, in light data, so brightness of the star, you can infer the presence of a transiting body. In fact, it's a very useful measurement, because you can imagine if you had a much bigger planet, you'd have a much bigger drop in flux. And so in fact, you can actually measure the relative radius of the planet to that of its star by just looking at the depth of the transit. Okay, so now this is still a tough measurement, but it's easy. Easy done. It's for a Jupiter going across the sun in transit, you get a 1% relative drop in its brightness. For the Earth, it's tougher. It's 1/100th of a percent. But we can still do this with modern telescopes and modern CCDs. And so once it was known that these hot Jupiters had a fairly good chance of being detected in transit, scientists went out with a sample of radial velocity planets that we already knew they were hot Jupiters and just went and saw, was there a transit that occurred? And we didn't have to wait long. The first transiting planet, which is HD 209458, yeah, the names are not very interesting. Every now and then I'll make up a name for them and make it a little more fun. But this one was discovered in 1999 by Dave Charbonneau, who's here at the CFA. And that's exactly what he did. They predicted a time that it should be crossing in front of its star. And they went up with telescopes, and they just measured the brightness over time, and they had this data. Okay, so again, this is brightness as a function of time. And this is the movie up there just to show you what's going on. And so they took 2 separate transit events, and they saw a little bitty dip. And so this system was favorably aligned. And not only that, since we have the transit now, and we have the radial velocity, we get a mass and a radius. So now we can say something very specific about this planet. Okay, so this was a very successful discovery, and it motivated more searches with transit. So now instead of using this radial velocity method, which takes a lot of time, big telescopes, very fancy equipment, why don't we just use some small 10-centimeter telescopes, look at the brightest stars, and just take a picture of them every now and then and get their brightness level? And this is what these ground-based surveys came in. There are a bunch of different surveys with funny names like Ogle and Trace, which is actually hosted here at the CFA, WASP, EXO, HAT, which is the Hungarian automated telescope. But these are all very successful, and you can see, as these came on, there's a little jump. These have discovered a number of planets, but by the nature of them, they're on the ground, so obviously you can't stare at stars all the time. And you have to pick, you have to say, okay, we'll look at these 100 brightest stars, and we'll jump from one star to the other. And so you're really not going to be able to do much more discovery than these hot Jupiters, these guys that are close enough that you're likely to see their transits. So prior to Kepler, which I'll describe in just a second, our knowledge of transiting planets was really limited to these real big, really close in. So this is orbital period down here. This is the size relative to Earth. So up here is Jupiter. These were all really huge guys that were just cooking, all hot Jupiters. There's some exceptions, but the reason these long period ones worked is because they had really high eccentricity, so they dove into their star. So these things were already getting torched as well. All right, so again, we're limited to very large and very close. Okay, so then came the idea of Kepler. And really this all started with a very sweet man, Bill Barucki, who's at NASA Ames. And so even in the 80s, Bill Barucki had transit detection on the brain. And this is before hot Jupiters even existed. So he was thinking of actually detecting transits of solar system, like stellar systems. He didn't know hot Jupiters existed at all. But how could he do that? I just said, the chances of catching a transit is already really low. For an Earth, it's 1 in 200 for randomly oriented. But then again, that also presumes that every star has an Earth-like planet at an Earth-like distance. So, if it's 1 in 100 stars, then it's 1 in 20,000 chance, look at the math, right, of actually catching it in transit. And so the way to do this, which is how Bill Barucki thought this was simple, is just look at 100,000 stars all the time for 4 years. Okay? And so, of course, this sounded crazy, and when he proposed it, he got rejected 4 times in a row. So the way he suggested to do this now is very simple and very obvious. You can't do this from the ground. Weather and the sun get in the way. You need to stare continuously at a bunch of stars. And so the way you do this, and you leverage these large numbers, is you put a telescope in space, Kepler, and you just stare at one field. So this is an animation here. This is not real data, but the idea is that here's one star. It's actually oriented favorably, so we catch a transit. Okay, that's great. There's one, but most of them won't be oriented that way. Some will be on face, and we won't see any transits here. There'll be no detection of a planet, and so on and so forth. I think this animation goes for a while, but it just shows you the principle of Kepler is that if you look at enough stars, eventually you'll get lucky. Okay, and so how do we actually set up this system is we launch this telescope into space, and we put it on an orbit that's actually at the same distance as the Earth, but it's not around the Earth. We don't want the Earth to get in the way. So we put it in an orbit that trails behind the Earth, and we rotate the telescope every now and then so that the solar panels get some energy, and we don't fry the CCD. And you can see it's always staring in the same direction and staring at one single field of view. And so this is a modest telescope. It's a 1 meter aperture telescope. But in space, there's no atmosphere to bother you. And so this is kind of the cartoon. This is of our galaxy here. This is where the sun is out in its arm. And this is kind of the cone that we're looking through here. So it's a really small kind of field of view. But within that field of view are a lot of stars. Okay, so this is an animation of that. So near the constellation Cygnus, you'll see the Kepler field of view. And this is just the footprint of the CCDs. So they have this weird pattern. They're all twisted. But it's hard to see right now, but we'll zoom in here on a single panel. You can see how many stars on an individual CCD. A charge-coupled device. It's the same device that's used in your camera. It's a digital photometer, so it collects photons. Okay, you can just think of it. It takes pictures. Okay, and so within this huge field of view, there's millions of stars, but there's about 150,000 stars that are like our sun that are continuously monitored all the time for many years. And what I mean by that is every 30 minutes, Kepler takes a snapshot of this entire field. And with that data, we string it all together, and we look for transits. Okay, and this has been going on for 3.5 years, and it will continue going on for another 3 years. Okay, so Bill Barucki's dream came true. Like I said, it took 4 rejections initially. It was great science from the beginning. They just had to prove it to NASA. And so here's the actual Kepler. I like to call it a photometer. It's a telescope, the Kepler telescope. There's a guy in the bunny suit for scale. This is pretty much how it looks in orbit, too. There's a dust cover on, the solar panels in the back. And here's it being launched on a Delta rocket in 2009. So since then, Kepler really has delivered. And so we expected to find a lot of planets. We had some idea. We didn't quite know what the frequency of planets around sun-like stars were. Maybe it was 10% for Neptune-sized bodies. We didn't know. That was what Kepler wanted to know. Wanted to know the frequency, in particular the frequency of Earth analogs, mirror Earths. But it's done very well. So how well is it done? Does anybody know how many candidates Kepler's discovered? That's about right, yeah. So I actually know, I think I saw the updated spreadsheet. It's over 3,000, I think, by now. But so if you put this all in perspective, if you take that field of view, and then you take all the stars that have planets, you make them blink with the period of their planet and scale it up, this is kind of what the field looks like. So it's just populated with planetary systems. All those stars are flickering away with planets around them. So we found what we hoped we'd find. So then to go back to our original diagram that I showed you here. So pre-Kepler, we had all these boring, hot Jupiters. Well, they're not boring, of course. They're exciting. But we want to know really about, our systems more like our own, if they do exist. And now we've populated just a bit. This was of June 2010, and most recently, February. Okay? So just to see, Jupiter up here, and then suddenly we started creeping down. Oh, now we've got a lot of Neptunes in a class of planet that doesn't exist in the solar system, which is something with a 2 Earth radii, a super Earth. But they exist. There's no deficit of planets from here to here, from Earth to Neptune. And then most recently we've been creeping down here. Okay, and I was actually part of a discovery that found an object that's Mars size. That's kind of how far we're dipping down, and they'll be smaller to come. Okay, so that was the history and the introduction. So now I'm going to break, and I'm going to go into what have been really exciting and really unusual discoveries from Kepler. A lot of these I played a direct role in their discovery or characterization, so you can feel free to ask me more specific questions. But this is kind of just a run through what I think are the most exciting things in the form of movies and visualizations and fun little points. So first off, in 2010, we discovered a rather unusual world called Kepler 10. Now this is the face-on view again. It's a movie. I'll start in a second. This is a sun-like star, and this is the orbit of the planet. It's a very close-in planet again. It orbits its star in 20 hours. Okay, so its exo year is 20 hours. Okay, but this planet, unlike the hot Jupiters, was teeny. And teeny is relative. It's 1.4 times the radius of Earth. But being so close in, it's fairly superheated. So if there's a hot Jupiter, this is a hot super Earth. So I actually got kind of sick the first time I saw this. So hold on, it's kind of a roller coaster ride. But basically, it's so hot. Again, it's about 3,000 Fahrenheit. So then this is north of the boiling point of iron. And so since it's so close in, just like the moon's face is always facing, one side is facing towards Earth, this one's also synchronized. So one side of it just gets superheated. So it's a liquid surface. It's unambiguously rocky. In fact, it's the first unambiguously rocky exoplanet discovered. This is not snow. This is presumably ablated iron or so forth blowing off the surface because it's superheated. Okay, so now this is where it gets Disney-esque here. So we're kind of jump into it, and this is obviously artist rendering, but Tim Pyle at JPL does a really good job. So we're going to filter through the channels of liquid hot magma racing towards the substellar point where the sun is most hitting it, the star that is. There's a turn up here that I kind of got to look away for. Oh yeah, I know. Yeah, exactly. And so the point is that there's going to be this one side that's pretty much just liquid. I mean, we don't know this for a fact, but well, yeah, that's the one. But we know its mass and we know its radius, and so we can say something. The content must be mostly silicates with an iron core, just like the Earth. So it has an Earth-like composition, but it's superheated. Okay, so that was a fun one. All right, so that was in 2010. That was an exciting discovery. So again, we just saw the transit of it. We did some follow-up analysis. Do you have a question?
Yeah, how can they tell it's timing off?
It's expected, just because over time you expect energy to be dissipated in a way. If it was rotating that way, it would induce some large bulges on the planet, and those would try to slow it down in response. Okay, so we expect it. We don't actually know. Some ways you can tell if you as it orbits around, you see the bright face come into view, and you can measure that change in light. That's really hard for this guy because he's so small. Okay, so next up, and this one I was involved with. I was not involved with Kepler 10, but I just think it's a really cool movie. So this next one graced the cover of Nature, and this was really exciting. So there had been radial velocity surveys that have discovered multiple planets around a single star, but there never had been, until Kepler, multiple planets in transit around one star. And so this is what Kepler provided. And in extreme fashion, this was a planet with 6 systems, all that transit. Okay, so just keep in your mind that you've got to make it so the viewing angle is such that you see all these planets that are all spaced out and period. And you can imagine that either it has to be really well aligned with we're right in the plane with it, or they're all really close to their star. And in this case, these guys were very, very close to the star. So this is another great Tim Pyle movie. So this is the star. And so first, we're way far away. We're looking as Kepler does, and look for the twinkle of the transits. So it'll blink. Oh, there, see some planets in transit. And now we're going to zoom in. This one's not vomit-inducing. And we see the radii are scaled up so you can see, and you'll see the last planet come zooming in a second. Whoa, that's good. Okay, and then you'll see the orbits in a face-down view with nice little trails so you don't lose them. Okay, so all of these planets Now, we're used to, thus far, hot Jupiters and hot super-Earths having orbital periods less than 5 days. These were much, much longer. They had periods up to 118 days. Okay? But the majority of them were within 50 days. Okay? But these were all smaller bodies, but they weren't super small. These weren't little BB rocks. These were Neptune size. 4 Earth radii is roughly a Neptune radius. So this guy was kind of small, but all the rest were fairly big. Now, these were packed in. And to give you a perspective, here's the orbit of Kepler 11. This is the most external guy at about 120 days. And then if you superimpose it down on the solar system, these 5 planets all sit within the orbit of Mercury. Okay, only the outer guy is external. And so this is an extremely compact system. And for this to work, these things must have formed in a very regular way. They couldn't have interacted with each other and kicked each other out. They had to play nice. And so this system is extremely dynamically compact, we say. Okay, so that's exciting. We have yet to break the Kepler 11 record for transiting systems, although I do know of another one that breaks it. It's not published yet. Okay. So next up, so now moving, all the rest of this is I've played either a direct role in the discovery or an important role, so please ask me questions. So next we go to the movies, okay? So this is an iconic scene from Star Wars. This is Luke looking pensively towards a double sunset on Tatooine. And so Tatooine is a planet, and does anybody know what the system's described as? Circumbinary, does that make sense? Okay, it's a circumbinary. So there's 2 stars in the center. So instead of having just 1 star in the center, 1 sun like we do, you have two stars. And those stars are orbiting about each other. But then there's a planet out here that's orbiting around the center of mass of both of those guys. And that was the vision that George Lucas had. And so obviously it'd be really exciting if this exists in reality. And in fact, it does. And we have an awesome movie again from Tim Pyle. And so this is Kepler 16. This was the first transiting circumbinary planet, but it was really the first unambiguous example of a transiting circumbinary planet. So here is the planet we're looking over at the top. There's this more massive star, about 70% the mass of the Sun. The smaller star, which is about 20% the mass of the Sun. And so you can see that it's kind of hard in this perspective, but you can see the planets going around both. I'll show a different perspective in a second. So this is a really exciting discovery. I announced it, when did I do that? Last September in Jackson Hole at a conference called Extreme Solar Systems, which makes sense, I think. And in fact, we asked George Lucas to sit on the press conference, and he was going to until the last day. And he backed out. Luckily, we had John Knoll, who's the president of Industrial Light and Magic, who came and sat on. Okay, so again, I don't know why this movie's so jittery, sorry. But this is looking top-down now, so you can see the planet over here. And so this is what I was describing. So the 2 stars are doing their own thing. They're actually pretty much unaware of that planet. They're being perturbed a little bit by the tidal field of the gravity of this planet and forcing it. This planet is certainly feeling those 2 stars. And it's going on more or less a circular orbit, but because there's 2 stars, it doesn't actually close. Okay, and so just some more details here. I'll give you, this is the frozen view. So here's Kepler 16b out here. These 2 guys orbit one another every 41 days, whereas Kepler 16 is out on a 230-day orbit. So it takes 230 days to go around. It's about the size of Saturn. And again, these stars are a little bit smaller, but they're not too different. The difference in size between the 2 is more relevant. Okay, so this was really exciting, and I'll go into detail about how we actually did this. But there's some great art that came out of this. It was great in the news. And yes, we did formally buy the rights to that scene from Lucasfilms, and we do call it Tatooine. Although I don't think it's fair, because in the Tatooine case, I think those stars are supposed to both be G stars, so like our sun, but this one obviously has a really teeny little M dwarf and then a K star. So it's not quite the same. I'll show you an example in a second that makes it a little bit better. Okay, so now this is the nitty gritty. Okay, so this is a movie that I made. So again, you'll note the differences between high quality NASA productions and what I made on my laptop. But this actually shows the data. It shows exactly what we actually saw. Okay, so just to describe the panels down here. So it's going to be a moving display here, but this is the actual light curve data. So again, this is brightness and then time. And you see these little gray points are the actual Kepler data. And then up here we have a bunch of simulated views with some niceties that I put in. We can't obviously see them, we can't see spots, but I put them in there for fun. So right here is that same top-down view, but the radii are big and inflated. And then we have the view as Kepler would see of the stellar binary. So we're centered right on the center of mass of those 2 stars. And then planet B is out here. I'm pointing over there, and it's orbiting around. And then the other things you want to stay focused on are, these are astrocentric. So we're staring at the center of star A, staring at the center of star B, and then staring at the center of planet B. And you'll see these things evolve over time. It's kind of a boring movie, so I'll stop it after a little bit, but you get the idea. Okay, so in the data, we actually see the eclipses of the stars. So in a second, star B is going to pass over star A. And we get this big dip, okay, because the star B is a significant fraction of the radius of star A. And then, because this movie is so boring outside of it, I made it speed up here. And so then B comes zooming in, and we'll slow down again in a second. And so now B is going to cross across star A. And just as, there it goes. So it made a small dip, but it's not too different from the dip you're going to see in just a second, and just a little bit of little b. I'll show you in a second. So this is going to speed up now, and actually it's going to catch back up with the smaller star B, and it's getting ready to transit star B. If you can see it in the data, it's right there, but it actually crosses it. And the scale here is crazy, but we measured that, and it's actually important in constraining the system. And then eventually, star B will come back, and it will pass behind star A this time and get completely blocked out. So all of its light's reduced, and it goes away. Okay, so then this continues ad nauseum for a while. But this is, so just to be clear, this is what we actually measure. This is all I see. And so when we saw this, we had to think about it a little bit, and we said, well, the planet seems to be crossing at irregular intervals. It must be circumbinary. And so by carefully modeling it with some dynamical algorithms, we can say exactly what the masses and radii of all of these components are. And in fact, it became one of the precise measurements of a planet ever discovered. Okay, so as soon as Kepler, I'll let it run while I talk. As soon as Kepler 16, which was in September, was discovered and announced, we immediately started thinking, well, is Kepler 16 all alone? I mean, are these things just incredibly rare and we just got really lucky? We didn't have to wait long. In fact, after the Jackson Hole meeting at the Extreme Solar System meeting that announced this, I got an email about 5 days later from Bill Welsh at San Diego State, and he said, okay, we have 2 more. And so we immediately worked on those 2 more, and we published them, I think, 3 months later. And those were Kepler 34 and 35. So these are just, I don't have another fancy movie, but I think Kepler 16 did the trick. But these are the artistic renderings by Lynette Cook. And so these are more true Tatooines, I would say. In the case of Kepler 34 and 35, these guys are almost solar mass, and they're almost equal mass. Okay, so the first thing that we got out of this was that, okay, circumbinary planets are not rare. And in fact, just based upon the sample we have, we don't have that many eclipsing binaries. We had already found 3 circumbinary planets. They must be around at least 1% of stars that are in a binary formation like Kepler 16 or 34 and 35. Another interesting thing we started thinking about is we wondered, you know, these planets are around 2 stars. We're usually thinking about habitability around 1 star. And habitability around 1 star, usually we refer to that as being where the range of distances from the star with which liquid water can exist on the surface of the planet. So for the Earth, the situation's fairly boring. It stays at roughly, a global average stays roughly at a uniform temperature. Of course, there's seasons, and that's due to the rotation of the Earth and its tilt relative to the ecliptic. And so that we get seasons that way. But in a circumbinary system, the situation's quite different. So here's the hypothetical system. This could be Kepler 34, 35, or 16, or the other ones I'll show. But the planet is more or less orbiting around the center of mass of the whole system. And these stars are orbiting around the center of mass of the whole system. And so sometimes the star in the binary is close to the planet, and sometimes it's farther away, and sometimes they're both right here, or maybe one's here, and I can actually play this. And what happens is that the temperature varies on the time scale of the binary. And so if these binaries, in the case of Kepler 16, it's 41 days. In the case of 34, it's 28, 35, it's 21 days. And so you have seasonal variations on your planet on the order of a month. Okay, so you're going from in some cases spring to summer, in some cases winter to summer. Okay, so this is an unusual setup, and we're not quite sure how to deal with the atmospheric dynamics. What does this mean for habitability when the habitable zone is doing this the whole time? So this is a very exciting development. And we got to actually think more deeply about this with the most recent discovery. So again, we've been very busy in the last year since we discovered Kepler 16. We discovered 6 additional systems and 7 planets. And the reason that we have a different number there is because Kepler 47 was discovered. Now, what was unique about Kepler 47 is that there was 2 planets in the system. And they were both roughly coplanar. So the inner planet, in this case, so the stellar binary orbited around one another every 7.5 days. The inner planet about on 50 days. And then the larger outer planet around 300 days. Okay, so what's interesting in this case is this is pretty much a sun-like star. This is a much smaller star. It's like 35% the mass of our sun. And so it's really not adding that much light. So in this case, if you have an object that's at 300 days and you have a star that's about the size of the sun and emits the same amount of light, this happened to be a planet in a habitable zone. Okay, so this was the first habitable zone circumbinary planet, the outer one. Of course, it's a big object, so it's probably not very amenable to life, maybe Carl Sagan-esque floating creatures in the atmosphere, but we don't suppose. Maybe there's a moon around it, and it's a rocky moon, and then it supports life. But this is in the so-called habitable zone. And so this system experiences these rather unusual seasonal variations on the order of 8 days, because the stars are moving around every 8 days. Okay, and so then there's one more circumbinary planet. So I've actually worked on every discovered transiting circumbinary planet, and the most recent one, which we announced, I think, a month ago, is called PH1, which is Planet Hunters 1. So does anybody know what Planet Hunters is? No? Okay. So there's a website you can go to, planethunters.org, and on that website you can look through Kepler data, and you can look yourself to find dips. And so what actually happened is that this was one of those systems that we didn't discover. A citizen scientist looked in the data and said, oh, that looks like a circumbinary planet, and he told us, and sure enough it was, and he's an author on the paper. Okay, now what's really interesting about this system is that there's the two stars that you're used to, and what you're used to now in this last 30 minutes, with the planet going around it, but there's also two more stars up there. There's the website, by the way. And so this is actually a 4-star system. These two binaries, this binary in the distance is about 1,000 AU away, so 1,000 Earth-Sun separations away, and this whole system is bound together gravitationally. So we've gone from expecting 1-star systems to having 4-star systems. Okay, so this is recent and exciting. So that's the circumbinary planets. Does anybody have any questions on the circumbinary planets? Okay. No? Yes, yeah, go ahead.
So how does this system work? Like, all 4 stars orbit one center of gravity?
That's correct.
Or all 4 stars?
Nope. The planet is circumbinary. So it's around this binary. And then this whole system, this collection of 3, its center of mass is in orbit with the center of mass of that binary system. So it's a hierarchy. There's always a hierarchy. We haven't yet found, to find 4 stars and a planet around that would be some crazy stuff. That probably would become a rogue planet pretty quickly. Right. Okay. Is there any other questions? Happy to take questions. Yeah?
How would such a system work?
That's a good question.
From a planetary disk, but 2 stars, so...
It's tough. In fact, we're still not quite sure. But there's some clues in what we've discovered thus far. The reason it would be tough is simply because you can imagine you have these 2 stars that are kind of stirring up the pot. And so it's a very tumultuous disk. Everything's being smashed together and being ground up. And so usually in the case of a single star, things can aggregate. They can smash and stick. And eventually when they get big enough, they can gravitationally attract other bodies. In the case of circumbinary systems, the mean velocity of all these components is high. And so they smash together and they don't really form very well. They don't stick together. So in fact, what we suspect is that these planets formed much further away where it wasn't so tumultuous, and then they migrated in. And in fact, we found, every one of these systems that we found, all the planets seem to be sitting right on the edge of stability. If they went any further in, they'd be ejected from the system. And so it seems to be that these things form far away, migrate in, and then stop right before they can't go any further. Okay. I'm going to go on, so you have more questions afterwards. Okay, so I'm going to change topics to my last, and this one I discovered the planet and did the analysis, and so this is a really cool system. Very happy with it. But first, let's return to the solar system, and again we have this tidy perspective. We think, we thought all solar systems were the same. They look like this. You have the terrestrial bodies in here, and then at a more distant spacing you have these giant planets, and these 2 groups don't really mingle. Okay, the terrestrial bodies are down here. The giant bodies are way out here. This is a cool thing I grabbed from Wikipedia. It kind of puts the distances of the planets on a football field, putting the sun at the 0-yard line and then Neptune at 100 yards. And you can see how they're spaced out. And I guess on this football field, if you put everything to scale, the sun would be the size of a golf ball, and the gas giants would be the size of BBs. So that just gives you kind of expanse of empty space. Okay, so we expect rocky planets, terrestrial planets should be interior, all the big guys should be out, and they shouldn't play with one another. And so then I found Kepler 36, which is an odd couple. So this, again, is the data. So you get a chance to take a look exactly at the data. So up here is all the data. It's pretty boring, but can you see the little comb of dips? And so that's transits, repeating transits of this guy. So this is planet C in the system, and its exterior. And I looked in the data a little bit more carefully, and I found another planet, which is planet B, which has this really small little dip. In fact, if you compare the radii of these two, it suggests that they're about 2.5, factor 2.5 different. Okay, so this is planet B in transit, and planet C in transit. So this is not too exciting. We find a lot of systems where there's a small body and there's a big body. So what was shocking about this system is the time it took these planets to go around their stars. So planet B finished its exo year in 13.84 days. Planet C finished its exo year in 16.23 days. Okay, so the ratio of the two periods of the system is basically 7 to 6. So these guys are uber close together. And so how close together? So I have a couple scale plots to show you how close they really are together. So you first of all, they're still close in. So at those short orbital periods, they're still much closer than Mercury is to the Sun. But you see, so the radii have been scaled relative to the star, but they're relative to each other for the planets, and the orbital distances are the correct scale. So you can see how tightly spaced these two guys are. They're still very close compared to Mercury. Another way you can put it is you take the two closest bodies in the solar system, which would be Venus and the Earth. They're 20 times closer than Venus and Earth are. And keep in mind that B is a super-Earth, whereas C is a Neptune. Okay, so you're putting this ice giant, possible ice giant, it could also be a super-Earth with a big cloud of hydrogen and helium, right next to a rocky body. So this was actually the second unambiguous rocky planet that Kepler has discovered. We measured the mass of this guy extremely well, as I'll try to explain. Okay, so I'm going to try to do this. I have a demo here of some software called Celestia. Has anybody ever used Celestia? It's really fun. If you have a chance to download it, it's free. And it helps you simulate stellar systems. You can look at the solar system. So I can do this quickly. All right, 1 second. Okay, all right. So I'm going to move this back over now. There we go. Okay, so this is the Kepler 36 system. All right, so with Celestia, you can actually input the coordinates of these things. You can give them surfaces. You can give the stars different brightnesses. And then you can evolve them, which is most fun. So I can move these guys along. All right, so this is sped up, obviously, but this is the scale of the orbit. Again, it's much smaller than Mercury. And you can see these guys orbiting. So what's interesting about this, guys, is that they're not always close together. Let's see if I can make this work. They're not always close together, but occasionally, in fact, every 100 days, they come to a close approach. Okay? It's simply because their period ratios eventually lead to that way. Every 7 orbits of the inner guy and every 6 orbits of the outer guy, they'll come real close together. So what I'm going to do is I'm going to, if I can stop real quick, I'm going to center, hopefully, there we go. I'm going to follow that and center it. Okay. And so now, and zoom out, hopefully. All right. So now what I'm going to do is, instead of focusing on the star, which we were doing a second ago, I'm going to focus and make it sit in a fixed frame relative to planet B. Okay. And then I might speed it up here, actually. All right. Speed it up. Okay. And now I'm going to take the orbits away. And so now you watch this dance. C comes in and gives a little kiss to B. All right, every now and then. So this happens every 100 days. It comes in. It'll come in a second. Come in real close and say, oh, there we go. Okay? And so this effect is very important. It's actually measurable. Their interactions measurable in the data. So every single time they come real close to each other, they give each other a gravitational kick. They change their periods appreciably, enough that we can measure it in the data. And then they just kind of go about their own way for the rest of the 100 days. They just coast along, and then every now and then they get this real close and get this real quick click. Okay, so now I'm going to stop that.
Is that stable long term?
You can ask me about that later. It is stable for some solutions that match the data. Okay. It exists, right? So it must be. It may not live long. No, we think it's long-term stable. Okay, so now how close do these guys get? So I showed you the picture right here. They look really close right there. They get within 1 million miles of each other. The best perspective I have is they come within 5 Earth-Moon distances. So that's really quite close. And so when they get close together, you can imagine that there's great tides welled up on each of the planets, much in the same way that the Earth's oceans are tidally forced by the moon. And we have this great artwork by Dave Aguilar here at the CFA that shows the rocky and potentially volcanic surface of planet B as it looks towards planet C at their closest approach. Now, obviously, this doesn't really give the closeness much fairness, because I mean, obviously, you could have a telephoto lens centered on that and zoom in. But here's a more relevant example that I like to show. Okay, so this is a beautiful picture of Boston with a full moon. So you can imagine, instead of this being Boston, let's just say this is a hypothetical city on planet B. Okay, and so then you'd be looking from planet B out to planet C. And so at their furthest separation, planet C would appear as something 1/6 the angular size of the full moon over Boston. But then over this 100 days, they come to their closest approach. And when it comes to its closest approach, it'll be 3 times the angular size of the full moon on Earth. So it looks something like this. And every 100 days, you would see this effect. So it would zoom away and then come into view. Okay. This is a little, if you're curious, this is a little keynote trickery I did. I'm pretty proud of it. So if you note, I think, let's see here. If you note, the water actually gets brighter. I'm not going to give away all my secrets. Okay, so that's actually all I have. So I was just going to go over some of these exciting things. So thank you very much. There's some exciting results from Kepler. There's some more to come soon enough.